but it just puts out something into the entirety of the universe, which I'll draw for the moment as just kind of some soup. And we call this pervasive influence to the edge of the universe the electric field. This is the electric field of this charge. Now, that right there obviously should bother you. What is it that's being put out in here? This is nothingness, okay? There's nothing here. And yet I'm saying that this charge is able to give that point in space some property called the electric field. Now, if you can, for the moment, say, okay, fine, let's move on to see how it helps us over here. If we are looking at little q, the lowercase q, we can say that little q has no idea about the existence of another charge a million miles away. It is simply reacting to the local conditions of the space that it is sitting in, and that space, for reasons unknown, has this thing called an electric field. Okay? So this feels, so the effect is that Q feels a force from the local electric field. So, what have we really done here? We've really thrust this idea of why these two charges know about each other to repel, and we put it all on this middleman called the electric field. So we say that this charge puts out an electric field everywhere without having any idea if anything heeds the call, and then this charge reacts to the local electric field having no idea why the local conditions are the way they are. So if this, the cause, is the electric field made by big Q, the effect is that Q feels a force from it. I said they were both positive charges. So for instance, in this case, that force would be something like this. So essentially, it's putting everything on this middleman, the electric field. It's a way of cleaving cause and effect into two different parts. We can talk about the cause without having to worry about what it's affecting. We can just talk about the electric field on its own. And we can talk about the effect without necessarily having to worry about the cause. So we can talk about why little q feels the force that it does. Well, it's because of the local conditions of the field, not because it has some kind of knowledge of some charge far, far away. Okay? Now, you notice that I've drawn it with this being the cause, this feeling the effect, and therefore the force is attached here. Of course, you can say everything in reverse as well. It's a mutual force of attraction or repulsion. So could you say that little q makes its electric field everywhere, and then big Q sits in that field and feels a force? Yes, you can. You can say everything in reverse. So that's where the labeling comes in, capital Q and lowercase q. For me, the nomenclature that I use is capital Q is things that make fields, that I'm interested in them making, what fields they make, and little q's are the things I care about on the effect side, even though everything happens in reverse. Okay? So that's the labeling scheme that I use, just so you understand which direction I care about the interaction, even though everything is always a mutual thing. Okay? So let me try to give you an analogy of how we're shifting our perspective. In the force perspective, everything is a direct interaction. Okay? Whereas in the electric field picture, charge interaction happens through this middleman. So let's imagine that the floor of this classroom was made out of a big mattress, a big bouncy mattress. Okay? So if I walked in this room and I was hopping around like this and making, shaking around the mattress, your desk would start going like this. And if someone asked you, why is your desk jostling around, you would point, my weirdo teacher is jumping around over there. That's why my desk is shaking. So you're talking in the direct perspective. You're talking in the force perspective. This idea that what's happening to you is a direct cause of that thing over there doing that other thing. So that's the same thing we have here. So let me instead imagine that same scenario, but you have a blindfold on. So you're just sitting in your desk, and your desk is jostling around. If someone says, why is your desk jostling around? You're more likely to attribute it to a local condition. So you might say, the reason why my desk is jostling around is because the mattress that my desk is sitting on is jostling around. So you're just basically saying, the thing that I am, local conditions where I am, where my desk is, that is the cause of what's happening. Because ultimately, if you have a blindfold on, you don't know if it's me jumping around or one of your classmates, or there's an earthquake. You have no idea. You're just stating the facts, right? That the ground underneath you, your local conditions, are the cause of what's happening to you. That's the difference in the field perspective. We say that this charge feels a force because of the local conditions of the field, okay? So notice it's not that the answer is any different. Your desk is still jostling around, but the difference is how you just tend to describe that. Now, it's a good analogy, but it's not a perfect analogy. Here's why. When you say that your desk is bouncing around, that's because there is something there to be affected. There is a mattress is made out of fabric and springs and things like that. But here, there's absolutely nothing here. So the electric field is an influence on nothing. So that seems weird. How can we be so sure that there is something here? When you have a mattress, you can say, hey, there's fabric and springs over there, even if they're not jostling, they're not moving. But here, this is completely empty space. How can we be so sure that the electric field is not just right where this charge is located, but everywhere in the universe? If we set a charge down here, it'll certainly feel a force, but how can we say, well, maybe the electric field came into being, swooped in there to exert a force on that charge when I put it there, but it wasn't there beforehand. It's kind of like that old riddle, right? If a tree falls in the forest and there's no one there to hear it, does it make a sound? Have you heard that? Okay. The answer, by the way, is yes, because there can still be a longitudinal compression of the air molecules there, okay, as you learned in the end of Physics 1. But this is a much more apt scenario because there is truly nothing here. So this is where I report to you that we choose in our human model to assume that the electric field is everywhere. It is everywhere where there are charges to be affected by it, and it's also in places where there doesn't happen to be anything to actually push on. Okay, so that's the electric field model. Okay. So basically what we have is that these two charges in this model don't talk directly anymore. Everything happens through the electric field. One makes electric field, the other one feels electric field. Okay, it's like when a couple is no longer getting along, right? They talk through the divorce lawyer, right? They don't talk directly anymore. So one person gives the divorce lawyer a document and the other one gets it from them. That's the electric field. It's the divorce lawyer, okay? So that's kind of a little bit about just what is the conceptual side of what's going on. Now we're going to go ahead and firm it up quantitatively with the reminder that everything we get has to agree with Coulomb's law, because this is no more, this is not different physics, it's the same perspective, a different perspective on the same physics. So it's cleaving apart charge interaction into cause and effect, but the end result has to be the same. It's just a new perspective, it's not new math. So let's figure it out. So we're basically going to cleave Coulomb's law apart into cause of the electric field and the effect, field of force. from the electric field. And again, for my purposes of labeling, the charge which I care about being the cause is capital Q. The thing that feels the force will be lowercase q. So the electric field, we need to talk about its size. We need to talk about its direction. And then, of course, the force experienced, we're going to have to also discuss what is the size, what is the direction. So what I want to do, I need to fill in all four of these things, size and direction for both things. And I'm just going to kind of go in the order that I think makes the most sense, starting with the size part of the force. So that's the size equation. Notice, first of all, that just because I want to talk about size only, I want to wipe out any sign that might possibly creep in there. There are two vectors involved, force and electric field. And since they're written without vector hats, that just means size of. And then charge, of course, charge isn't a vector, but charge can be negative, so I put an absolute value sign around that to make sure that that doesn't muck things up. So let's bounce that out over here and examine it. What's going on here? Well, basically, the electric field here is the property of the space. So it is a property of the location where this charge happens to be. So it's the property of space of where this charge is located. So someone has gone to the trouble of finding out what is the space like where you're about to put this charge. Why is the property of space like that? Maybe there's another charge, or maybe 20 million other charges around, but for some reason the space is like that. And the only thing that you have to do is specify what are you going to put there. This is the amount of charge that is placed there. So you take what the space is like, multiply it by what you decide to put there, and the equation will yield to you how much force that charge will feel. So this is, we could say, is a property of the charge, or more properly on the charge. It's a force felt by this charge, by being placed here. So you take what the space is like, multiply by what you put there, and it will tell you how that thing reacts to the space, the amount of force it feels. This equation is enough to deduce what is the units of electric field. The units of electric field must be newtons per coulomb. So if it helps numerically, for instance, let's say we have a location in space where the electric field is 10 newtons per coulomb. Then we decide that we're going to put at that location a 1 coulomb of charge. 1 coulomb of charge, how much force will it feel? 10 newtons, right? The coulombs cancels. And so a 1 coulomb charge placed at a location with this property, 10 newtons per coulomb, will feel a force of 10 newtons from its local space. Now, this again, the units being newtons per coulomb, you can see they work out perfectly. That's another way to visualize electric field. You can think of it as it tells you how many newtons of force are available per coulomb at a given spatial location. So since our local electric field in my example was 10 newtons per coulomb, that means that there will be 10 newtons of force that act for every coulomb that you put there. Now the amount of force is not going to be the same, because if I take that exact same spatial location and I instead put 2 coulombs there, how much force will that feel? That will feel 20 newtons. So there is no one answer for the amount of force at this location. It depends on what you put there. But the common theme is that this spatial location has this property of 10 newtons per coulomb. And then it's up to you what you decide you want to put there. For instance, if you have 10 newtons per coulomb, and then you put in a neutron, which has no charge, then that will feel no force at all. We still choose to say that the space is like that. The space has a property of 10 newtons per coulomb, but here there's no coulombs to pull on. So that is the formula for the size of the electric field. Are there any questions on that? Okay, so let's move forward. So I guess let me skip from this one all the way across to this one. Let me talk about the direction of the electric field. Now, so far I've drawn it as a green soup, which conveys the idea that it goes out to the entire universe, but it carries no information other than that. The squiggles just basically say it's there. So there's got to be a way to draw this influence in a way that carries more information. So let's go ahead and do that. So let's make it a positive charge. Again, use my green pen, but I'm going to replace the soup with something better. So here's what I do. By convention, and I emphasize this is by convention, this is ultimately a human model for discussing the situation. By convention, it is agreed that the electric field is drawn as a series of lines that are radial to the charge. Looks like this. In the case of a positive charge, it goes radially away. So I'll fill that in right here. For a positive charge, the electric field is radially away. So make sure you understand, this is not 8 forces pulling on this charge. In fact, maybe this charge is the only charge in the entire universe. There's nothing else to be pulling on it. This is a way to map what is the pervasive influence to eternity that this thing has. It's everywhere, but we need to draw a sampling of lines only. There's electric field here too, even though there's no line. You can't just sneak up to this thing between the lines, okay? But if we drew it everywhere as a soup, then we can't draw any information along with it, okay? So, if we do this, if we choose to do it this way, then, of course, that's going to have consequences on the effect side. So for instance, if we choose to do it this way, let's drop in a little q that's positive. Now you, as the omniscient viewer that can see all the charges involved, you know which direction this charge is going to feel a force. Which way? Feel a force to the right, like repel. So that's the force picture. You just look at the charges and somehow they know how to interact across some distance. But let's think locally now. So let's say that this charge does not have any information about the world at large. It just simply is aware of the electric field sitting where it's located. And at the local location, the electric field points to the right, and it also feels a force to the right. So we are forced to conclude then that positive charges feel a force in the same direction as the electric field. I like to call them as it's quote unquote downstream. Okay? Feels a force downstream to the electric field. Now, that was simply a consequence of overlaying our knowledge that like charges repel. It makes sense, right? We've just chosen the electric field lines to go away from positive charges, positive big Q. Well, of course, other positive charges want to get away from big Q too, so they point the same way. Force and field point the same way. Okay? So that is simply a way to make sure if we're going to choose this, then this is a consequence. Otherwise, our like charges won't repel. That would be weird. You can drop a positive charge anywhere in here, and it'll, of course, repel, and that force will be along the field line. So let's try a minus charge. I don't know, let's drop it in right here. Now, as the omniscient viewer, you can already tell, how are these two going to react to each other? They're going to attract. So this little Q is going to feel a force like that. Or we can think locally. We can think of it as that whatever the local field is, the minus charges feel a force upstream or against the field. So minus charges feel a force in the opposite direction as the electric field or upstream. They're the salmon of charges. Now this is an incredibly useful thing to know because if you know the local electric field, you have no idea why it is what it is, but you can nonetheless say a lot. For instance, if you know the local electric field looks like this, and no idea why it is, obviously it's due to charge or charges somewhere else, but if you know the local conditions, if you drop a positive charge in there, it'll feel a force like this. If you drop a minus charge, it'll feel a force like that. So knowing about local conditions is like 90% of the battle. Then finding the force is really straightforward. You just have to multiply in what you dropped in there. Okay? The only accommodation we need to make sure that this is preserved on these direction rules are preserved on the effect side is just to make sure that when we have a minus charge like this, we draw that the field lines are radial but pointing inward. Like this. So everything flows from that first convention we picked. The positive charge having the electric field point radially away, it means that minus charge, that better be radially toward. And if we do that, I will leave it to you. Let me just quickly sketch it. A positive charge would again feel a force with the field, and a negative charge would again feel a force against the field. So everything on the effect side is preserved. So what I want to point out is that these direction conventions, I know it seems like there are twice as many, and that's because there are. We've cause and effect apart. But they do not produce anything more than opposites attract and like repel. They're entirely consistent with the same stuff we already said. There's just twice as many rules because we need to be able to talk about direction consistently on only the cause side and direction on the effect side as well, independently. Okay. So that right there is all the direction stuff. And as far as the final one of the force things to fill in here, we of course need to fill in the size of the electric field. So let's go ahead and figure that out. This has to be consistent with Coulomb's law as well. So this is the field picture where little q feels a force because of the local conditions of the field. And in the force picture, which better be consistent, of course, the amount of force is determined simply by the Coulomb's law. So we just go ahead and go in here and realize that the only way these are going to be equal is if this is equal to this. Otherwise, it wouldn't match up. You get a different answer for the force depending on which perspective you were in, which would be weird because nature doesn't have a perspective. These are human beings wanting different points of view. So, here we have it. Here's the equation for the electric field made by the cube. This is the pervasive influence going into the entirety of the universe, and the amount of influence will, number one, be determined by the amount of charge. You can see that if the charge is bigger, then the electric field at any given location is bigger. So bigger charges are bigger things to note, and small or vanishingly small charges make very little influence. But all of them, whatever influence you make, it dies with distance, right? So the reason why a charge feels less force when you go further